Hi everyone, welcome to the next episode. This is rotational momentum. I just gotta dry this for a second, hold on. I don't want to be running ink on smeared water. Alright. It's always good to use towels whenever you wipe stuff down because it saves the environment. It's better for trees. Anyway, this episode is, we're going to be doing rotational momentum, which is actually the last episode on rotation. We're not quite at the end of Newtonian mechanics. I'll let you know when we get to the end. Other than that, when we get into Kepler's laws, I'm going to show you the Japanese connection with parabolas when they were studying comets and things like that. Other than that, let's not get too far ahead of ourselves. We're not worried about this. We're dealing with rotation, so we want to deal with things that rotate and spin. We don't care about orbits yet. Just focus on things that can rotate, like we did in the last episode. The last episode we did was rotational kinematics, and the way this rotational stuff works is it's kind of like repeats of doing the linear stuff. So rotational kinematics is like redoing 1D kinematics and 2D kinematics, and then rotational, and then we also had to talk about force to inertia, mass to inertia. So in rotational momentum, we kind of bring back momentum again, and force and energy and all that stuff. Okay. We're going to get started with determinants. That's really the best way for me to show you vectors. We're going to do it through linear algebra. I'm going to change it up. I'm going to spice it up a little bit. I'm going to make it different. So instead of just running right to vectors, we're going to do some matrices. And trust me on this, this is a really good idea to do this. I thought about doing this video, and I think matrices is really the way to go. I forgot my iPad. Right back. I gotta get my tablet. Now somebody gave me a comment saying I should buy a $100 speaker and a $100 Bluetooth pen. It ain't gonna happen. I mean, this is season 1. So if I do buy that equipment, I mean, possibly I'll get it when I do sound, but I'm not going to buy a Bluetooth pen. I'll probably just get a soundproof speaker. Other than that, the speaker quality sounds decent. And like I said, this is just a starter video season. This is like our first season. So we're going to go easy. I'm going to show you determinants. It's really the way to go with this. I'll tell you a brief story about determinants. So determinants were something that were actually disproven in Japan. Matrices actually came from China, and then they were brought over to Japan. And Japan actually kept a lot of the European math outside of themselves. They didn't want any European influence. So I read the history of Japanese mathematics, and believe it or not, they didn't really get European influence till the 1700s. They had what was called the Wasan period, which is W-A-S-A-N, which was a mathematical period. But unfortunately, when Sekikawa was their mathematician, they weren't really well suited for math. I read the entire book. This book that I have was written in 1912, of course, the year the Titanic sank, but gives you a really good story about Japan. And they ended their it talks about when the feudalism ended in 1868, when they had the end of the samurai. But honestly, I think the samurai still lives on. I don't think there's no more samurais left. There's descendants of samurais, and there's also probably hidden groups that we don't know about, maybe. And the thing is with the samurais, it's illegal in Japan, but only in Japan it's illegal. It's not illegal anywhere else. So rotation is like a huge thing. I'm going to have an episode on the center of gravity. but I'm not going to include it on this. We're going to actually do that before we hit gravitation, before we do black holes. Next episode will be a little small episode, like 5 or 10 minutes long. It'll be on gravitation. It's not really physics. It's more just plain old mathematics. So the story of determinants is they were never really in China. They were in Japan. Sekikawa figured them out by using an infinite series. That's the biggest thing that they had in Japan, was using an infinite series and mensuration of the circle. Infinite series can go anywhere. It can go in mostly India, but Japan had a special, unique way of using geometric properties with infinite series. They did what was called the mensuration of a circle, which is just measuring a circle by putting chords across it and all the weird stuff. They even did mensuration of ellipses, so they did it all. Conics is something that probably will be added with the next episode. I will do a brief demo on conics because I have to explain to you the center of gravity, and I can only do it using a cone. So that's how the Japanese did it, is they were big on geometry. But determinants were ran by a system of equations. So Japan had them with who their mathematician was, Sekikawa, and during his time, he didn't get very far. He could have gotten further than he was at, but he just didn't because of the fact that they didn't really know math in the samurai families. I mean, they only had certain ones that knew math. But Sekikawa knew determinants, and Leibniz is also known as the creator of determinants. He's important here. And the reason why I say he's important is because all we talk about is Newton. We talk about Galileo and then we talk about Newton, but we don't talk about Leibniz. Leibniz came up with the collisions, and he came up with the determinant method. So what a determinant does is it tells you if the linear transformation can be achieved. It tells you whether the matrix is invertible or not. I don't really like spoiling the tricks. I'd rather just show you the tricks before I explain the work. So, let me show you what I mean by a determinant. We're going to start by a 5 by 5. And whenever we're in the linear matrix world and we talk about 5 columns by 5 rows, we're talking about, I don't know if it's rows by columns or columns by rows. I don't know which one it goes first, but the way a determinant works is it has to have the same number of columns and the same number of rows. It cannot have more columns than rows or more rows than columns. Because if you have more rows than columns, then you have what's called the Gram-Schmidt. When you have more columns than rows, you have what's known as a vector form. Now, the funny thing with linear multiplication is I can multiply with less, I think it's less number of columns, but it has to have more rows. I can have the same amount of rows with less columns, but I can't have more rows with less columns. It has to be, I think, more columns and less rows. So, for instance, let's just use x's. X can be any integer value. I think this pen works. So if I have a matrix, we're going to use X. Or not even X, let's just do an asterisk. So if I have a matrix that has this, if I can multiply it, I can multiply it like something like this. See, if you notice, it has the same number of rows, but less columns. It's a rule. But I cannot multiply this times this. It's a rule in the linear world. This will not work. Has to have the same number of rows, but less columns. It can't have more columns and less rows. So a column is this, a row is this. And there's two types of row reduction, which I didn't really explain to you. The one we did was just simple row reduction. The other one is known as echelon form, which is the stair. In French, it means the staircase, but it works. It usually works where if you have a bunch of zeros. Echelon is when you go from the bottom to the top. You wouldn't believe how hot it is in here. It's like 86 degrees. Other than that, I showed you multiplication. Okay. We got to get started with determinants. It's really the only way I can explain to you how the cross product works, but bear with me. This is going to take us to linear. Well, we have to take linear algebra to get into rotational momentum. I think I have to connect to the Wi-Fi with my iPad. Where are we? The good news is I have just enough battery on here to show you this. Wi-Fi. I'm still here. I just have to pull this up. Okay. Surprised I'm not signed into this thing. I must have got signed out. I'm trying to give you a solution for come on. I think I hit sign up by mistake instead of log in. Okay. Linear algebra. I need to show chapter 3 where we do determinants. Let's see, chapter 3. I'm still here. I'm just trying to pull it out. It's doing technology is a pain in the ass. I'll tell you that. I mean, I have to pull crap up. It's not introduction. I believe it's properties. This one's good. This is a 5 by. Now this is a 4 by 4. Just give me a minute. We're going to start with a 5 by 5. I'm not doing a 4 by 4. Let's do a 5 by 5. Why is it putting me back to chapter 6? Let's do number 13. Okay. I'm still getting a 4 by 4. Let's see what 15 looks like. All right, maybe they changed the book or something. All right, it's a 5 by 5. I think I'm in the right chapter. I don't even think this is right. Hold on. It might be introduction. I might have the wrong. Oh yeah, you know what? We have the wrong chat. We have the wrong section. I apologize. It's introduction to determinants. It's the chapter I doubt it would be. Just bear with me. I'm still here. I'm not in the right example though. Just give me one. Sorry about this. I didn't plan on using this book. It's actually Introduction to Determinants. I was misguided on this. I know, it's number 14. Just hold on. Let's do 13. All right. So sorry about that. So sorry. Took me 4 minutes probably to find this. Okay. I mean, I would only be able to explain it without pulling up a solution if I'm actively taking the course. But I haven't, I haven't been taking it actively. So, I mean, I just took it fresh out of it. But all right. So whenever we do a determinant, we have to use what's called absolute value. So if I put an x inside, We have an absolute value. Other than that, you're going to have these numbers. Now I'm going to start with a 5 by 5. And then we're going to do a 4 by 4. I may not even do the math when I go to a 4 by 4. I'll show you a shortcut. I just would rather take a higher dimension problem and do that one by hand. All right, 5, 9, 3, 0, 4, 2, -1. How many numbers is that? 4. We just need one more column. -5, 0, -8. And listen, teachers use solution manuals. There's nothing wrong with using a solution manual. I mean, they're not at all a problem. Like, it's normal to use them. And when you get into grad school, a lot of times these are like the holy grail. Having these is like the fountain of youth. I mean, you want these. All right, so this is what we call a determinant. This is a specialized matrix, because if you remember before when I showed you a standard matrix, you always use little brackets like this. But if you notice, the lines aren't closed, they're in an absolute value form. So they're in what's called a determinant. So what you're going to do is some sort of row reduction, where I want to make these numbers 0, so I add a 2. Second row expansion. I'm trying to see how they get a -2. Huh. Where is there a -2? I'm guessing they're using this number down here on the corner. So somehow we get a -2 times 4, 7, 5, 0, 0, 3, 0, 0. See what happens with the number, if you notice, 3, 4, 2, -1. And then you have -5, -8, -3, 2. So you notice it gives me a value, and then if I do that, if you notice the dimensions are getting smaller, so instead of having a 5 by 5, we have a 4 by 4. And then this turns into, if I reduce this further, this turns to -2 times 3 times 4, 5, 0, 3, 2, -1, -5, -3, 2. And at this point, you would run the cross product. So if you do, at this point, you would run the cross product, which at this point, you would do what's called a vector product, which I'll show you what that is later. So it's -6 times 4, 2, -3, -1, 2. I'm not really sure how they done this, because when I did it, I just, I used the calculator, but I'd have to learn it from a book. -5 times 3, -5, -1, 2. And then this ends up equaling to negative 6, 4 times 4 minus 3 minus 5 times 6 minus 5, which is equal to 6. There's a quick way to do this. Don't worry about the next two. Don't worry about the next example I'm going to do, the 4x4. There's a nice quick way to do it. All right, so if I'm in a rush, right, and I really want to know the number, and I want to know this 5x5, there's a way to do this. There's a shortcut method. You have to go to linear algebra, and then you have to hit 3. You have to hit determinant, and then you have to create a matrix. So we're going to do 5 dimensions. In these kind of examples, you don't go any higher than 5. And it's interesting in the 5 degrees because I don't know if you ever heard of Horner's method, but in Japan they have what's known as Horner's method. When you have a 5th degree polynomial, it's basically synthetic division. So I hated long division, and I still do. I have to like study it. It's one of my Achilles heel. It's tough. A lot of times when you do algebra, long division is not a nice thing to work with. So a lot of times, and there's software now, like you can actually get if you use like there's computer software now like MathWay or Symbolab that'll actually show you how to do long division and stuff like that. But I have to, like, whenever I have time, I got to do that. But the fact is, I suck at it. So a lot of times, I was lucky enough when I was in pre-calc, I used Horner's method, which is basically synthetic division. I'll do a video on Horner's method, but it was something that the Chinese were trying to work on that they kept failing to do, and they finally succeeded in Japan. It's basically Horner's method and synthetic division is the same thing. It was used in computer programming up till 1970, and then it was replaced by some Newtonian method. I found it, the Horner's method. Let's see, Horner's method. I mean, this ties into what we're learning. See, synthetic division is the same thing. It's not any different. So if you type in what is Horner's method on Wikipedia, it'll tell you. I don't need to know Java. Now, it was replaced by another type of math. It's basically long division. What is Horner's? Is Horner's method still used? This internet's not, it's very slow today. Oh, this is killing me, guys. I'm trying to find, like, if it was replaced by something. Let's see if I can find it. Must be on my phone or something. I'm trying to find, like, Horner's method. I think this was the video, or the link that I found. Oh, the Newton-Raphson. Sorry. My mind was spinning all over the place. So it was Horner's method is a type of math that was invented in 1819. And in Japan, they actually use this. It was used up till 1970. And then it was replaced by the Newtonian Raphson method. And I'll show you what Newton's Raphson method is. Just this internet's taking so slow. Okay, so Newton's Raphson method is if you're taking a line, and we did this in kinematics. So the Newton-Raphson method, and we've covered this already. It's if you have two lines, and you have a y and an x, right? And then you have, let's say you have a straight line. And we call this the y-x line. I'm actually creating the straight line. And let's say I put a point here. And then I have to make a curve. The straight line doesn't really work well. So if I have y and x, I try to do a straight line. It doesn't really work. So if I have some curve, right? If I have some curve, this is a really crude drawing. Okay. So this is a Newton-Raphson method. If I have some parabola, right? And let's say I put the point of intersection like right here. I'm so used to drawing straight lines that I'm forgetting how to draw curves. Okay, this would be a parabola. So if I took a point, if I took one point, I'd have something that looks like this, my slope. And then if I took another point, it would look something like this. And then once I get a second point, I would then take a slope that only goes below the curve. And then if I took another point, I would have this as my method of least squares. And then I would have another slope that goes in another angle. And then you would call this would be 0. We call this O for origin. And then this would be x2, x1, and then x initial. It's a little backwards than you think. And then this would be f of x2, f of x1, and then f of x initial. So that's the Newton-Raphson method, which this actually replaced Horner's method. This is still being currently used in computer programming. And it really just follows 1D kinematics. You could think of this as like a launch. This could be like some kind of a launch. Although in reality, you would never have a launch from the x direction and the y direction. A launch would go up and then kind of fall down. But you could think of this as like a launch. So this is the Newton-Raphson method, which was named after two people. This is more on physics. This synthetic division was used until 1970, and it's the same thing with the scattering matrix. I don't know why particularly they don't use the scattering matrix anymore. I showed it to you when we did, I think, linear momentum. Other than that, let me show you a quick way of getting this answer. I apologize, this took me a half hour. So what I can do is I can clock in the numbers. I can do this. And I'll show you how quicker it is to do this. Like, don't do it that way. I just was trying to define how to do this problem. -6, 5, 9. This is like the Speedy Gonzalez way. This method's a lot quicker. So we're in a 5th dimensional world right now. We're in 5 dimensions. But we're going to go all the way down to like pretty much like 2 dimensions by 3 dimensions. See, when I punch that in, I get 6. Now this will work even with a 4x4. I just need numbers. All right, so if I had a 4x4, I can do the same. Don't really do it this way. It's easier to just clock the numbers in. If you are going to do it this way, make sure you read some kind of computer software. I'm just kind of experimenting. So if I do a 4x4, I can do the same thing. And then once we get to a 3x3, we can do the cross product, but usually it works better if we have a 2x2. And there's no 2x2 numbers. So menu 7, 3, so we're doing a 4x4 now. So let's do 6, 1, 2, 8, 0, 7, 0, 3, 0, 2, 0, 1, 5, -5, 0, 8. All right, so this one now is a 4x4, and if I hit the enter, I'm gonna get 10. That's my determinant. Okay. And then if I do one more, and these can get smaller and smaller. There's no 2x2s. It would be nice if there were. Let me do one more. One more linear algebra problem. So let's do a 3x3. 3x3s are nice because we can do the cross product. I'm going to explain it in the next problem though. I'm not going to do it in this one because it's too complicated. I didn't get a determinant. I didn't hit the option. Hold on, menu 7, 3. -11. All right. I'm not getting 0, which is a problem. I want to get a 0. Menu 7, 1. Get 4, I try another one. That's all right. So if the number would have been 0, that would have meant that the matrix is non-invertible. What a determinant tells you is whether it's invertible or not, if you do a linear transformation. All right. And determinants actually help when you do differential equations, because then you can tell, is the graph one-to-one? Is it invertible or not? So if I wanted to explain what a linear transformation is, let me see if I can find this. The matrix of a linear transformation. So we can test it by rotating the graph and stuff like that. Just take the course on linear algebra. I recommend that. Linear transformations, though, are important in differential equations because then if you know the matrix is invertible or not, and if it does have a linear transformation, it tells you the differential equation problem is solvable. That's what I'm hypothesizing, so it makes that easier to understand. Other than that, I'm going to show you the vector product, or the cross product. It is the vector product. Okay. So, why did I show you determinants? You're going to want to know. And the reason why is because of the cross product. The cross product and the determinant is the same thing. However, the cross product and a determinant is like a special case. Just like synthetic division is a special case with long division. Cannot be used all the time, but it can be used on certain circumstances. So, the same as synthetic division is rooted from long division. It's based upon long division. It's the same ideology with the how the cross product is rooted from a determinant. That's why I was showing you that. And I'm going to do a separate video on synthetic division. Okay. So if you're ever taking college algebra or pre-calculus, you'll learn my method. Or the method, really. Horner's method. Okay, I'm going to show you the cross product now. I don't really want to do numbers. Nah, I'm not going to do numbers. I do have to show you zero though, that's the problem. Guess we'll have to do both. Alright, so this is known as the vector product, but it's really called the crossed product. Now earlier we learned this function. What is this? This is a scalar. A times B, if you have two vectors. If I want to do a cross, then I do A cross B. Now this kind of method actually came from China. I think it did. So I want to show you how would I solve a U cross V. You know what? We're going to do numbers. I am not going to do a definition. We're going to do numbers. So let's say if I want to do, ignore this. This is not important. I want to do U cross V. V cross U and V cross V. Now this is a quicker method of finding a determinant, but this only works if you have a 3x3. In this case, this is a 2x3. There's a special method if you do a 3x3, but we're just going to stick with the physics. We're going to stick with the calculus way. You have to move shit around and rotate it and stuff, but other than that, let's just do this. So if I want to do U cross V, well, first off, I need my vector product. So my definition of U cross V would be equal to, we always say I, J, K. And then the numbers I need is 1, -2, 1, 3, 1, -2. And I actually don't even have to look at the problem. I know how to do it this way. 1, -2, 1. I just need the numbers. 3, 1, -2. Okay, so to get started, I have to circle the variable that I need. But what I like to do is I like to repeat the process 3 times. So I'm gonna repeat this. But you have to have a minus. And then you have the same thing again. You have to repeat. The trick with the cross product is you got to repeat the problem twice. Or really 3 times. It's like Beetlejuice, Beetlejuice, Beetlejuice. I'm just kidding. So then I do it the 3rd time, I add. The cross product is always plus, minus, plus. That's the rule of the cross product. And this is following this order, plus, minus, plus. And then I do the same thing again. I'm actually not even looking at a solution. I'm doing this on my own. Because it's very easy. And what's nice with linear algebra, like I said, if you really know how to work out the algebra, you don't need a calculator. It's just with a 5x5, it would have been ridiculous. Okay. So if I want to do a cross product, I circle the one I want. And then I cross the neighboring ones out. I cross this out, and then I have to do a little X. It's always this times this minus this times this. And then I do the same thing. I circle the ones I want, and then I do the same method. This times this minus this times this. And then I cross this off. And this is this times this minus this times this. Okay. So if I pull out the I, it's going to give me negative 2, 1, 1, negative 2. 1, 1, 3, negative 2. 1, negative 2, 3, 1. Two, negative 2, right, which is 4. So this is going to be 4 minus 1. 1 times negative 2 is negative 2. So it's negative 2 minus 3, which is negative 5. Or you could just say negative 2 minus 3. If you notice, I'm just doing the multiplication before I do the subtraction. 1 times 1 is 1. This is plus 6. So then if you do the subtraction right, I think it matches. 4 minus 1, negative 2 minus 3, 1 plus 6. Wow, it matches. Doing this on my own. Okay. So this is going to be 3. You don't need a calculator for this. Like I said, if you know how to work out the linear algebra, with linear algebra, you don't even need a calculator. Now I'm going to multiply out these vectors to these numbers. So this would give me 3i hat minus or plus 5j hat, and then plus 7k hat, or no, 3i plus 5j minus plus 7k. And if you wanted to do a determinant, you would only be able to do it by a 2 by 2, but these are 3 determinants in a different direction. And all right, let's do 2 more parts. I'll show you how u cross v does not equal v cross u. Let me show you that. It's important to show you. So if I change up the multiplication, I change up the sign as well. So we did this one. Now we're going to work on the v cross u. Whoops. Oh, crap. I didn't realize I wrote on another piece of paper. Oh, well, I'll just leave it like that. It's fine. Yeah. Sorry about that. Let me just crinkle that up. So far we covered u cross v. Right, we did that. Now we're doing v cross u. I think that's what we're doing, right? Yeah. And then we said v cross u is equal to this. Just ignore this. And I need the numbers again. 3, 1, negative 2. 1, negative 2, 1. All right, and then you do the same thing. Remember, it's plus minus plus. I feel like we should do a 3 by 3. Okay. See, all we literally have to do is repeat the numbers 3 times. 1, negative 2, 1, 3, 1, negative 2. All right. And then I just do this little trick. Okay, and then if I do this, this becomes equal to... All right. 1 times 1 is 1. 2 times 2 is 4. 3 times 1 is 3, plus 2. Right, you know what? I'm going to have to uncrinkle that paper because I got to show you something here. Three times two, -2 is -6. Okay. All right, so then this gives me 5i minus 5j minus 6k. I think that's right. Oh, shit. 1 plus 4 is... This should have been 1 minus 4. Huh. Oh. My bad. Let me redo this. I know what I did wrong. This should be 1 minus 4 because it's the two negatives cancel, but then you're subtracting this. And then you have minus j times 3 times 1 is 3, and then plus 2, and then this is plus k times -6 minus 1, which gives me -3i minus 5j minus 7k. Now, if you notice, this equation is almost the same as v cross u, but you can see how the signs are different. So this is all positive. If you notice that this is positive, this is positive, this is positive, that's negative, that's negative, that's negative. There's like a sign change. Now let me show you what happens when you have v cross b. So we just did this one. There's one more part to this. So I'm not going to show you the proof or what it provides, but I'll sketch it out is what I'm going to do, but I'm not going to explain the math behind how it works because it's more, like I said, the best way to explain it is a determinant property. So if I want to do v cross v, and let's say this gives me ijk, and then we have 3, 1, -2, and then 3, 1, -2. This gives me a 0 vector, which tells me that this matrix is not invertible. Let me see if I can find a 3 by 3, because I want to do that, use that same method, but we just use it with a 3 by 3 problem. It's not Kramer's rule. We're not going to be using that. I mean, this really applies to Kramer's rule, volume, and linear transformation. You could do it with circles too. So like I could do a linear transformation. Like for instance, if I have like a graph of a circle, I can, if it's a flat circle, I can bend it and make it look like an ellipse. We call that a linear transform. This is what they call a linear transformation. For instance, if I have a circle that's got crossed lines inside, let's say it has grid lines. I know this looks more like an ellipse, so just bear with me. Let's say this is just a perfect circle. Now, if I want to take it in an angle, it'll look more like an ellipse. And then what would happen with the angle is this would stay the same. But then this part would bend. And whenever you take Jacobians, you'll learn like the UV plane. So if you ever take like, I don't know, Calc 3, you can call this the XY plane. And then you would call this the UV plane. Jacobians are very valuable. I feel like I should do like videos on integration, but Jacobians, they tell you something about, I forget what they tell you. I haven't really studied them currently, but they're important. Well, let me look up what a Jacobian can do, because that's just like a Jacobian. What is the purpose of a Jacobian? Generalizes the gradient of a scalar valued function is in several variables, which in turn generalizes the derivative of a scalar for the... Oh, it's used to represent transformations between coordinate systems or functions involving multiple variables. Don't worry about that. Just stick with that simple, plain and simple linear transformation. I'm not going to go. We're not dealing with multivariables in this whole season is not about multivariables. I'm not going to do that on here. Just think single variable when we do this. This is really just single variable math. It's really single variable calculus. Yeah, this textbook I have for linear algebra, it doesn't really show you. Oh. There is a method. You use the cofactor expansion. Oh, I see what they did. Got it. We're going to do that. I'm going to do the cofactor expansion. So if I want to do a cofactor expansion, it's really the same thing as the cross product. I would have to do this concept. This is what we call the cofactor expansion. So if I say that A, and let's say A is equal to 1, 2, 0, 5, 4, negative 2, 0, negative 1, 0. Now the cofactor expansion is the exact same thing as the cross product. It's the exact same thing. It's just a different word we use to describe it in linear algebra. But if I wanted to do the cofactor expansion, it follows a theorem. We say determinant A. Yeah, I'm not going to explain the theorem, but basically what would happen is we'd have to take the 0 part. Ow! They use the bottom numbers. So we'd take the 0, right? We'd start with the 0. And then we would say this is equal to 0. And then you would end up with this. So you'd have 0 times 5, 0, 4, negative 1. And we would know that's 0. And then that would have to be minus negative 2, which is just, yep, minus negative 2. So you'd have to use the bottom numbers, and then you would have to do 1, 0, 2, negative 1. And then plus 0. Oops. Determinant, you have to use an absolute value. Let me just fix this. 0, 5, 0, 4, negative 1, minus negative 2, 1, 0, 2, negative 1, plus 0, 1, 2, 5, 4. Okay. And then obviously this would give you 0 plus 2 times negative 1 plus 0, which equals negative 2. Now, if you ever have a determinant that tells you 0, that means the number's it's not invertible, which means it cannot have a linear transformation. But if it's a negative number, any non-zero negative number or positive number, it doesn't matter if it's negative or positive, as long as it's non-zero, it's invertible. Okay. I think I killed an hour doing some math. Sorry about that. Now we're going to move on to some physics. Oh, before I do, let me show you indeterminate analysis. So in Japan, they had a special thing. If you ever take Calculus 1, you're going to learn what an indeterminate is. So an indeterminate is like if I have 0 over 0. We call that an indeterminate. It doesn't mean the answer, this does not equal 0. What this stands for is that it's an indeterminate, so it can be any number. It could be 8 over 8, which would give you 1. It could be any value that we don't know. We call this an indeterminate. So indeterminate. What we just did is called a determinant. But an indeterminate is different. A determinant is a number that has to be non-zero that tells us if a linear transformation can be done or not, can be achieved successfully. If it's 0, like this case, that means that the matrix is not, it can't be transformed, or the graph function can't be transformed, but really we would just say the matrix. The matrix cannot be transformed if it's 0. An indeterminate's a little different. It's if you have something that's 0 over 0. So this will pull hair out of your head in case I haven't showed you. If 0 over 1 is always 0. But then 1 over 0 is infinity. Because when I divide by nothing, I explode the whole function. But 0 over 0 is what we call an indeterminate, and it's not equal to 0. It doesn't mean it's 0, we just don't know what it equals to. So 0 over 0 is what we call a determinant. I have nothing and I'm dividing by nothing. There actually is something. It's something over something. We just don't know what that something is. See, in India, 0 is known as a placeholder. Brahmagupta discovered it's a placeholder. That's indeterminate analysis. Well, that is what an indeterminate is. So in Japan, they wanted to perform what was called an indeterminate analysis. And I want to show you what it looks like. It's like a chart that's used to check if something has an indeterminate or not. I don't know if it's in this chapter. Let me see where it is in the index. Okay, so they have indeterminate equations. equations, this is it. This is indeterminate analysis. So they ran it by using the mensuration of circles. That's how indeterminate analysis was done in Japan. It's a chart, and it's 1, 2, 3, 4, 1, 2, 3, 4, 5. It's a, well, you would say it's a 5 by 4, which is like a vector form. If this was a matrix, this would be like a vector form. But this is known as indeterminate analysis. They use circles and triangles and semicircles. All right. Yeah, they showed you math too, for indeterminate equations. I'm trying to see what other pages there are. $182. See. Yeah, I'm not going to go there. All right. We're done with that. That's indeterminate analysis. Let's get into physics. We're only going to do one problem, which will make up the time for this video. Okay. I think I'm way too far. So they call it dynamics of rotational motion. It's the same thing, it's rotational momentum. Which I'm gonna just fix that by calling this whole thing angular momentum. Well, rotational momentum. Because remember I said rotational? Okay, so before I get started with this, let me show you something that you need to know. There isn't going to be any torque in these problems, so don't worry about torque. I will show you the relationship. So position, remember, becomes theta. And we call this side the linear, and we call this the angular. So it's like the linear world versus the angular world, but you can think of it more as a reflection. So this is from linear to, this is from linear to angular. So x becomes theta. V becomes omega. A becomes alpha. And we could do vectors if we'd like, but it's better to not do vectors. I realized it. Mass becomes inertia. That's what I showed you so far. X becomes theta, V becomes omega, A becomes alpha, M becomes I. So you have X, theta, velocity, angular velocity, acceleration, angular acceleration, mass, inertia. And this is in radians, radians per second squared. And then I think it's kilograms or something, meters squared. I forget what inertia is. But there's one more I didn't show you. So if you have force, this becomes torque. So there's one more that's involved. And whenever we talk about energy properties, we really care about the mass to the inertia and the force to the torque. Although energy is in everything. So let's get started with one example. I'm trying to think why there's an ohm in here. I think because you're supposed to use a little omega, and they use a big omega to show you. Oh, so in this problem's a spinning gyroscope. You have a larger angular velocity and a smaller one, and the large omega Has nothing to do with resistance. You're going to see big omega is measured in ohms, which I call it ohms. But it's ohms, and because if you get electrocuted, you go, it's a joke. It's measured in ohms, but it's weird that they're using a big omega in angular, in rotational momentum. It is weird that they're using ohms for this. Because ohms, we'll talk about ohms when we get into season 3, which is electricity and magnetism. I'm actually going to just do one season on sound. I'm not going to combine it. Because I feel like I could just do I could do just 3 videos on the next season, and we'll get right into season 4. I'm going to take a differential equations course before I even get to into sound. Alright, so let's just get started with the math. I'm not going to read the problem. I did enough of that already. So we're almost done. I know it looks like a long video, but we're almost done. This will end any second. Any minute we'll be done, believe me. Okay, so we got omega is equal to WR, and I guess W stands for weight and R stands for radius, over 1 ohm, which is then equal to, and just say it's an ohm, which is equal to mgr, which it's over 1 omega, and that's equal to mgr over m r squared over 2 times omega. And then that equals to 2 gr over r squared omega. So this is the theory of the problem. Ignore the linear transfer. Maybe important, but we don't need it. This is the problem that we're dealing with. We throw some numbers in here, right? We say, actually, I'm going to show you what omega is. Be careful not to use omega and omega. The precession, we call it the precession angular speed. That's what this big omega is. And another thing too is you get torque is equal to R cross W. Follows the cross product. All right, and then the omega, we have to do a little system of equations. So omega is equal to 1 rev over 4 seconds, which is then equal to 2 pi radians. So we say 2 pi radians over 4 seconds. Right? Yep. Which is 1.57 radians per second. All right. And then you got to know the inertia. So there's one more equation. Whoops. This is a very touchy tripod. There's one more equation I got to show you. Inertia is equal to 1/2 mr squared. R just stands for the bigger radius. That's what R stands for. All right, now we're ready for the problem we're dealing with. So G is a gravitational acceleration due to gravity, which is an approximated value of 9.8. It's not exact, it's approximate. So this omega, not to get confused here, we're actually running this. I'm plugging this in. 2gr over r squared omega. Okay, so that's equal to 2 times 9.8 meters per second squared times the inner radius, which you could just say is 2 centimeters. And then you divide that by 3 centimeters squared. And then multiply that by 1.57 radians per second. So this is little r, And then this is big R. And then this is little g. And then this is omega, which is known as the processional angular velocity, or processional rotational speed. To sound more fancy, we'll just say processional rotational speed. Yeah, this is processional rotational speed. And then this is acceleration due to gravity. Acceleration due to gravity. I don't like saying processional angular speed. I like saying I like how this sounds. Processional rotational speed. Okay. That is the omega. Which, if you run the math, you're going to end up getting 280 radians per second, which is equivalent to, or defined as, 2,600 revolutions per minute. Which is actually known, this is defined as an RPM. If you ever have a record and you have 33 1/3, means it takes 33 1/3 revolutions per minute. Or if you have a 45, it takes 45 revolutions per minute. 78 revolutions per minute. Sometimes you'll have a 16 revolutions per minute, which spins slower than a 33 1/3, but it should run the same amount of speed because it's the same size of a 45 record. Okay. So now, all I have to show you, and I don't know why they use weight, that's confusing. Now we just have to go through the summaries. See, we're pretty much done. The only thing, I'm not going to do diagrams. Let me see. Give me 1 second. See if we want to do diagrams. Yeah, why not? I'm going to do it on the lever arm. I'm not going to do it on the other ones, but I'll do it on the lever arm because it's very complicated and I feel like we should understand this. So, to understand torque, we say that this is equal to R cross F. Torque is equal to, we call this rotational momentum cross force. And then if you wanted to just do it without vectors, you would then say torque is equal to force times length. Okay. And then if you had a lever arm, you're going to see it turning. And then there's some point of origin, which is really right here. And then you would say that F tangent is equal to F sine phi. And then here, you then say the F radial force is equal to F cos phi. And then if you ran the geometry, I'll re-sketch this. We call this phi. L is equal to R sine phi. And we call this the lever arm. Can't even do the arm right. Okay. So what I was trying to sketch you was something like this. was trying to sketch you this, and I screwed up on the drawings. All right, that's what I was trying to draw. Okay. And then if you want to say the sum of the torques, you say the sum, that's a crappy looking sigma. The sum of the torque pointing in the z direction is equal to inertia alpha z, which z means it's pointing up and down. You can think of it that way. In this camera, it's better to explain Z. It's really, Z's not going up and down. It's really going this direction and this direction. It's pointing out and toward, because the other two were just going on a sheet. But the best way on a camera angle, since we're filming, is, and I'm not actually showing this to you in person, think of Z as it's coming this way would be the positive direction, and then going in would be the negative direction. And the reason why that's important is because when we get electricity and magnetism, especially with electricity, it's going to pave the way to understand that. You'll get a head start. Okay. Now we're going to get into, so I just showed you torque and rotational dynamics. Now we're going to do combined translation and rotation. So we translate it by using the concept of kinetic energy. So we then say that K is equal to 1/2 m center of mass squared plus 1/2 inertia center of mass squared, which we say calm. Oh, it's times omega squared. I forgot a little omega. It's all right. I fixed it. So it's K is equal to 1/2 velocity center of mass squared plus 1/2 I center of mass times omega squared. Ignore this little blot in between. It's, and I'll rewrite it. What the hell? So this is a relationship between the linear world and the rotational world. But we use the center, we use kinetic energy, we use conservation of energy. This is a capital K, by the way. It stands for kinetic energy. It's energy in motion. Kinetic energy is like chasing a dragon. It's pretty much easier. Well, it's difficult. All right, so that's the kinetic energy. And I'm out of space here, but this is all the same stuff. So then you're going to say that the sum of the external force is equal to mass times the center of mass times the acceleration. And this is another property that explains the relationship between linear and rotational. And then the second one is the sum of the torque and the z direction. These are separate equations, by the way, but they're all in the same group. Sum of the torque in the z direction is equal to the inertia, the center of mass of inertia, times acceleration z direction. And then we say v, center of mass of the speed, is equal to r omega, and that's rolling without slipping. That's called rolling motion. If we want to do rolling motion, we use that equation. Now I have to show you work done by a torque. So when we talk about work is what is always applies into force, but we have to explain it using a line integral. So work is equal to the line integral from theta 1 to theta 2 of tau z d theta. And this is still an FTC integral. This doesn't change. And since it's an FTC integral, we then say work is equal to torque z times theta final, or theta 2 minus theta 1, which is equal to torque z times the change of theta. So they imagine these as 2 points. And if you want to call this initial and you want to call this final, be my guess. I mean, I'm just changing it. That would make this final and then that initial. It's not a theta, it's actually a 0, which we call that naught. It's one better way to think about it. And that's constant torque only. Okay. And then the total work is equal to 1/2 inertia omega final squared minus 1/2 omega initial squared. And then we say that the rotational momentum, which we call it P and not L. Did we use L for linear momentum? God, I can't even remember. I gotta find out. Hold on. Conservation of momentum. I know we didn't use M because that's mass. I know we used P for momentum, but I guess for rotational momentum, they're still using P. So you're just saying P, rotational momentum is equal to torque Z times omega Z, which is anything pointing in the Z direction. All right. And now if you have angular momentum, that was work done by torque. What?
Can you plug the fan in?
Yeah, doing a video. So angular momentum is length is equal to R cross P, which is position cross momentum. So this is linear momentum, I think, which is equal to R cross MV. So length is equal to position cross momentum, which is equal to position cross mass times speed. It's confusing because when you think of linear momentum, it's always P. But for some reason, they're saying it's also P for angular. I guess because of the fact that angular, it's like a buildup of the linear world. Okay. And then at the end, we say that length is equal to inertia. Oops, that inertia is a scalar just like mass. I made that little mistake. Length is equal to inertia times the angular speed. And that's rigid body rotating about axis of symmetry. And then we say that the sum of the torque is equal to d length dt. Derivative of length with the time derivative. Okay. I'm going to show you one more summary. I have to show you stress and strain. That's the next summary I got to show you. So I'm only going to show you collisions for equilibrium. The rest of it, it's really for fluids, which is probably going to be season 4 is thermodynamics, or season 5. It'll be season 4. So I'm only going to show you like part of this. I'm not going to show you the whole thing. And this is actually will be good when we get into gravitation, which will be the next episode. Okay, so if you say the sum of the force of the x direction is equal to 0, this is actually Newton's third law. Newton's first law. Actually, this is Newton's first law. This is Newton's first law. So the sum of the force in the x direction is equal to 0. I'll put a comma there. Sum of the force in the y direction is equal to 0. And then I can't fit the third one, but I'll put it below. Sum of the force in the z direction is equal to 0. The z direction is equal to 0. So then we say that the sum of the torque is equal to 0. And you make this a 0 vector. All right, and then if you want to say center of mass, then the center, actually I'm going to write it down here. So the center of mass,
Yes.
hold on, I'm doing a video. Stop it. So center of mass is equal to M1, position 1, plus M2, position 2, plus M3, position 3, plus so forth, divided by M1 plus M2 plus M3 plus so forth. And that's an infinite series. So center of mass, we talked about it before. It's if you have some object and you have to look at the center of it. When we get into center of gravity, I will show you the geometric description of this formula, of this equation here. This will tie in perfectly with Newton's third law, and it'll help us get to like gravitation and black holes and all that such. Okay, so next video we're going to do is center of gravity, which is basically the same thing as center of mass. I have to show you that, and then I might show you acceleration due to gravity. I suppose I could add that in there, show you all the a vector we learned. That way it prepares us for gravitation. I'll show you all that, and I'll show you Newton's laws and all that stuff. The next episode will be more like a review. It won't be really like textbook stuff. The one after that we're going to do is just gravitation, which is Newton's fourth law. There's actually a fourth one that Newton created. That's why he's so popular in physics. That's why I called the season Newtonian mechanics. And then after I show you that last final law, that's pretty much when Newtonian mechanics comes to an end, is gravitation. Because we don't completely understand gravity. After that, I'll do like Kepler's laws, comets. We'll do problems like that, and they go with black holes and the Schwarzschild radius, which will be the final episode. There's going to be a bonus episode, and I'm not going to tell you what it is. Maybe when we get into black holes, I will. Nah, I won't. So there's going to be one more after that one. So that we're talking about a short one on the next one, and then the following one will be a standard one, and then there'll be 2 standard ones. So we're going to have about probably 4 more episodes. All right. Thank you. Bye.